Probably. All right, hey Daniel. I am not doing the related rates like the whatever 3-4, section 3-4 homework from the book. So I'm gonna have to give this to you when you get back. This is like 6 homework problems. It's a front and a back. And we're gonna do like some of the, well, we'll do the first one together, and then I'll have you guys kind of like we do in normal fashion, like you guys go and then I'll go, okay? Because yeah, that goes pretty well in here actually. So I'll record all of this, but if you need to skip ahead, certainly do. Number 1. First of all, before we get to number 1, things that you need to look for. I always look for an equation, what I know, and what I'm trying to find. That so helps me like break this problem down a little bit. Okay, what the equation that you're using, what you know, and what you're trying to find hugely helps out. Okay, all right. Water is leaking onto a floor and it forms a circular pool. Okay, so I know I'm dealing with a circle, right? Okay. Now, technically, we're not going to get too into this too much, but if it's leaking out into a circular pool, technically, it does have a thickness, right? So, like dealing with a cylinder with a really tiny height, okay? But I think in this case, they're just looking for the area of the top of it, right? Okay. The radius of the pool increases at a rate of blah, blah, blah. How fast is the area of the pool increasing? So we're only talking about the top of the area. So not taking into consideration that there is a depth to this water, right? But like technically it would have a very, very small depth. True? Make sense? Whatever. All right, so we're just talking about the area of the pool. All right, water is leaking onto the floor in a circular pool. So equation. You already said it. What equation are we using?
I forgot.
Area of a circle.
DRDT.
No. Area equals
ARDT.
pi r squared. That's my area. That's my area formula equation. All right. The radius of the pool increases at a rate. So radius, the rate of the radius is 4. That's what?
DRDT.
DRDT. Yep. And that is 4. Okay. All right. How fast is the area increasing? That's the rate of the area that we're trying to find. What's that called? The rate that the area changes.
ARDT.
DADT.
Oh, why am I switching the letters?
I don't know. DADT. That's what we're trying to find, right? The rate that the area changes with respect to time. When the radius is 5. So we're looking specifically when the radius is 5 because we know that a lot of times the radius will, especially for area, as the water starts, the radius increases really fast and then it slowly like goes out from there. Even though the water is flowing onto the pool, the volume is like coming out at the same amount. The radius increases really fast and then it goes slow, kind of like inflating a balloon, right? Okay, so at the instance when the radius is 5, what is all this doing? All right, now what? Got all my stuff filled out. Cool.
This is weird.
Now what? Derivative. Okay, let's do the derivative of this guy. Derivative of A. dAdt. Everything is with respect to time. dAdt equals. All right, pi r squared. What is my strategy for finding that? Do I have to use the product rule?
No.
How's come?
Because
Pi is a number.
It's just
Yep,
a number.
pi is a constant. Pi is just a number. So we only have one variable, so I don't have to use the product rule. I can use the power rule, right? 2 comes down in front. Pi r to the first power times DRDT. We have to have DRDT. Okay. All right, good. Now we plop stuff in. We are trying to find dAdt, so that is nice. Okay, equals 2 pi. The radius is 5. DRDT is 4. We don't have to do any hard work. 5 times 4 is 20, and 20 times 2 is 40 pi. And give me that number. Approximately.
125.7.
125.7. And this is the area changing. Okay, so what's area? The rate that the area changes. 125.7 what per what?
Centimeters a min.
Square centimeters per minute? Min? Yeah. Square centimeters per minute. If this was volume, it would be cubic centimeters per minute, right? Or whatever, right? Okay, good? Okay, all right. Number 2.
Was that the answer?
That's it.
That was boring.
That was boring. That was so uneventful. You're just getting smarter at these. No. And what you're trying to find. Okay. All right, I'll get you started.
Yeah.
Oil is spilling from a ruptured tanker.
There?
Yeah, right below your knee.
Yeah, yeah.
On the chair. It's like long and frilly.
Okay. Oil is spilling from a ruptured tanker and spreads in a circle on the surface of the ocean. Circle. The area. We're talking about area of a circle. This is uneventful because this is the same as what it was before. Area equals pi r squared. All right, your turn. Go. I'll give you 10 seconds, 20 seconds,
get the
30 seconds,
microphone?
whatever. What?
We get the microphone?
No. You just do it. And then I will follow.
Okay, so let me do some thinking out loud here. So our rate is the area. Okay. And we need to figure out the radius, how fast the radius is changing.
When the radius is 10.
When the radius is 10. So basically, I'm just gonna go like.
Yep.
Like
Right.
9 pi equals. Right. Like 20 pi. Right. I think I lost myself. 20 pi.
I'm trying to find the pi.
20 pi DRET.
How fast is the radius increasing? So you're the rate of the radius is what you're trying to find. DRDT. Yep. What we know.
I don't like that they give us 2 pi's and one equation. Whoa,
But the pies are going to cancel, aren't they?
no.
They should,
Um,
right? Don't they? I don't know.
Yeah. Yeah, not to flex, but I did that way faster than you did.
What? I waited for you.
Mm-hmm.
I did.
Sure.
Mm-hmm.
You just don't want to admit I'm faster at math.
Sure. And I'm trying to show all my work. I could do these in my head if I wanted to.
Yeah.
Uh,
I don't
probs.
I don't believe you.
Robs. What's 9 over 20? I don't know.
should I did that completely?
0.45?
Oh, I subtracted.
Oh, well, let me make some room.
Subtracted.
0.45. Don't tell me.
So-
Meters per minute
Yeah.
is the rate that the radius is changing. Now, the radius will not always increase at that rate, right?
True.
The more it goes out, the lower that number gets, right? So
True.
as 20 minutes have gone by, or however long, that radius is maybe going to be changing at 0.1 meters per minute, right?
You could find out.
Yeah.
But
Right.
I'm not going to.
The volume at which the water or the oil comes out will maybe be consistent, right? But the rate at which everything else changes will not be. Okay, number 3, equation. What we know, what we're trying to find. All right, you see if you can figure this one out. I'm not going to give you anything. Okay, go. I'm not going to give you anything. You see if you can figure it out.
Chronic? Wait, conical.
Chronic.
I thought it said chronic.
Oh.
So Billy. What the heck is that?
No, I hate cones.
1/3.
Oh yeah, 1/3 power squared, I think.
Pi r squared h. Is that right? 1/3 pi r squared h.
Are we doing volume of a cup?
Yeah, we're
Of a
doing
cone?
cones.
Yep.
It's a conical
Alright.
cup.
Volume equals 1/3 pi r squared h. Oh, you gotta do your product rule.
Why'd you send us off on this one? Water height 2. dH dt. rate is the water vapor it took up when the water level is 80 centimeters. So we're solving for dVdt.
Radius is 8. C. I don't know what's going on,
The
man.
paper cup is 10 centimeters tall with a radius of 10.
Wait, DADT, is that what we're finding?
dV.
Oh, DVT.
I have to do the product rule.
DV?
How should I split this up? Wait, why do I have to do the product rule again?
Did anybody draw a picture?
No.
Why not? The cup is being filled with water. Okay.
We can do it in our heads.
I don't think so, because you're going to be missing some information. 10 centimeters tall,
I'm confused on why I have to do the product rule.
because you have two variables,
Which two?
R and H.
Don't we know?
Right, with a radius of 10. Oh, this is a really wide cup. Not drawn to scale.
Isn't 8 the H?
What?
Water level.
But the H is going to change. So you have to take the derivative of him before you plug 8 in. Okay, let's back up. I know what I'm trying to find. I'm trying to find at what rate is the water being poured into the cup. What are we trying to find?
dVdt.
dVdt. That's what I'm trying to find. dV over dt. When the water level is 8 centimeters, what does that mean? Height. That means height, when the height is 8 centimeters. All right, I don't know what the 10 and the 10 have to do with it. That's what I'm starting with, right? Oh, the cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. What does that mean?
Rate.
The rate of what?
So DRDT or something.
The water level
The
rising.
level's the height. DH.
Level is the height, so this is dHdt. Okay? Now, the 10 and 10, I don't think you actually use any of that for what we're plugging in. We will use it to find what R is here in a second, but not to plug anything in. All right. Now, I have no idea if I'm missing things on my no portion. I don't know what I don't know, right? I don't know what I'm missing yet, right? Yeah. So what I'm going to do is I filled in as much as I think I can, right? Let's find the derivative and let's see what else we're missing, right? Okay. So what's the derivative of V?
Of V.
DV.
dV dt, right? Okay. I'm trying to find him, so great. Okay, we can have that. This, we have to use a product rule, right? This is F, and this is G. Got it? So F prime G plus G prime F. I'm going to run out of room. F prime G plus G prime F. Oofda. Okay, maybe I'll move my picture down. There we go. Okay. All right, F prime. That whole thing I'm designating as my F part. So I got to bring the 2 down in front. 2/3.
Pi R.
Pi R
DR.
d r dt. That's F prime. G is just H, right? Boop. Okay, what's G prime? What's the derivative of H?
DH.
Like 1 dH dt or just dH dt? Dang it, what'd you screw up? And F is all that stuff. 1/3 pi R squared. Okay, I'm going to clean it up and get rid of our parentheses here. dV dt. We have him accounted for because we don't know that. That's what we're trying to find, right? Okay, let's consolidate this stuff. I'm going to put the H in there, right? 2/3 pi R H dr dt. Do we know what R is? No, crap. We don't know that. Do we know what H is?
Yes.
Yes, that's 8, right? Is it 8?
Yeah.
Yeah. Do we know what dr dt is?
No.
Crap, we don't know what that is. Okay. Plus, so we got to figure out those things. Plus, I'm going to put this in the correct order. 1/3 pi R squared dH dt, right? I always put my dH dt's last for some reason. Do we know what R is?
No.
Could.
No. Do we know what dH dt is?
Yes. it's
Yes, it's 2. Okay, so I got some things to figure out. I got to figure out what R is. I got to figure out what dr dt is. All that good stuff. Okay, all right. The reason why they give me 10 and 10 is because they're saying that the radius of the cone will always be equal to the height at that point. So if my,
Fat cone.
right,
Sorry.
like it should be fat, like it's not drawn to scale. I should have made it fatter, but whatever. Okay. So they are saying that my water level is here at 8, right? Okay. So at that point, what's the radius of the cone?
Ocho.
Also 8, right? That's the reason why they gave me the 10 and 10. That means 8 and 8, right? Those are proportionate to each other. So from here, I know that R is 8, right? I know that. So the only thing I don't know now is DRDT, correct? And DVDT? Yeah, but DVDT is what we're solving for, right? Okay. But, we have the relationship that H is equal to R, true? The height is equal to the radius, right? Does that make sense? That's the relationship I have there. If I take the derivative of this, what's the derivative of H? DHDT. What's the derivative of R? DRDT. Okay, so now since H and R are the same, that means DHDT and DRDT are going to be the same, true? So I can plug 2 in for here, right? Because that's what DHDT is. I can plug them in there. Okay, all right, so I'm doing a little better now. DVDT, which is what we're solving for, is equal to, okay, don't plug any of the pi's and stuff in. I have 8 times 8 times 2. 8 times 8 is 64 times 2 is 128, yeah?
Minecraft numbers.
Okay, 128 times 2 again is 256 over 3 pi. Yeah? 256 over 3 pi. Plus, I have 8, but I have to square it, which is 64, times 2, 128, times 1/3. Yeah? 128 thirds pi? Does that compute? Sure? Are we following?
Yeah.
Okay, if I add those thirds together, thirds is that?
A lot.
384. I don't know. Check that.
Looks good to me.
Looks good to you? Does 384 divide by 3? Yes, it does.
Wait, let me think.
1,
Yes, it does.
2,
No.
128.
8.
Oh, I wanted
Did you do that in your head? Yeah, 128 pi, which is approximately.
No, nuts.
You have a calculator? Oh, okay. 128 pi, which is, of course, what is a decimal number?
The calc. Just got the calc on me.
402.
40 what?
402.
Point.
984.
No, it's 402, 460.
Well, let's go 0.1. I just want to put 1 decimal place on there so that I know it doesn't come out as a nice number. Does that make sense? Like, I want to make sure you don't know that it's 402 exactly. Okay, and that is what per what? We're dealing with volume.
Centimeter squared per second.
Centimeters cubed per second. Is it per second? Per second, right?
That's a lot
Second.
of porridge.
That is a lot of porridge.
Isn't that like oatmeal?
Yeah.
No, like a bit of porridge.
402.1 cubic centimeters.
Porridge.
Well, but a
Porridge.
cubic centimeter is like a mil, right? Isn't a cubic centimeter like a mil?
Oh, it is.
So that's not that much.
400 mil.
400 mils though? Like, I mean,
It's like
that's
half
not
of
that
a
much
million miles.
Dude, that's like.
per second. It's like a fire hose maybe coming out. I don't know.
I don't know.
How much liquid comes out of a fire hose? I don't know. This is a paper cup. Oh, it's being filled with water. Yeah, you definitely don't want to fill a paper cup with
And
fire hose
it
water.
And it looks stupid because it's a really wide cup.
Yeah, it is a really wide cup. Yeah, that like drawn to scale, it would actually be like, hold up, like that, because this height right here is the same as this length here.
It's a,
Oofda. Why would you drink from that? That would be silly. What's the correct ratio of height to width?
I think that's called
like a quarter. Like the radius is a quarter of the height.
I would say at the very least. I would say at the very least the radius would need to be half of the height, right? Like you could make a
At the
cup.
least or, like,
You
the
could
most?
make a cup that has like this length the same as this length, right?
I suppose.
At the least, but you should make it probably taller than that, right?
I think it is.
A quarter would be okay. A quarter might be too tall. Yeah, that would be double. Whatever.
I'm not thinking like
Okay.
tall cup.
It's a good thing we don't design paper cups, I guess, or something. I don't know.
And I hate.
But we
cone
could do it better
cups.
than what they did right
Why
here.
do they make cone cups? Those things are stupid.
Cone cups. I don't know. It like holds. I
Single
don't know.
use. You can't set it down.
Right. That's probably why.
Well, yeah.
Because you are forced to throw it in the trash can.
Like-
True? You
but,
can't set it down somewhere.
If I'm ever somewhere and I need a cone, how are you showing me that in the middle of math class? Show cometure.
No. I don't want to know. Oh, no. No.
Who did that?
Okay, here we go.
Katie Wiz Bravo.
Equation no find. Go. Okay.
Yeah.
You guys can do this. This one's an easy
I
one.
love spheres.
Spherical balloon. And we're talking about volume. So equation is
4/3 pi r cubed.
4/3 pi r cubed. Do you have to use the product rule?
No.
No. You guys can do this one. Go. I'll give you 20-second head start.
Really?
Really.
I don't know if I can.
Really.
Promise.
Find the DVD key.
Two over r centimeters a second. That's stupid. No, bless you's crazy work.
Because I didn't like this sneeze. And you asked for it first.
Haven't we already done this before?
What?
This one?
We've done a volume one before, yeah. So the derivative should look familiar.
Wait, what's r? Oh, silly me, I know what r is.
I don't have a calculator. Where did mine go?
That was nice of them. Tell me that equals that.
Mm-hmm. Do you know how to switch it?
Love cometure.
What'd you get? What'd you get? I can't read from that far.
Squint.
100.53?
Yep.
100.53 watt per watt?
Centimeters cubed a second.
Cubic centimeters per second. Because we're doing volume, right?
Are you gonna eat the school lunch today?
I don't even know what the school lunch is today.
Freaky fries? It's mummy dogs and freaky fries.
Oh, yeah. Okay, no. Probably
Sit
not.
in the fog machine.
You're gonna sit in the fog machine.
Can we bring that to the meeting?
Yeah, you can.
Okay, all right. 5. Equation, no find. Draw a picture first.
Is this the right triangle?
Probably.
Dang.
A 7-foot tall
That's
built
green.
person, oh gosh, is walking away from a 20-foot tall lamp post at a rate of 5 feet. I'll draw a picture of this. I'm gonna go lamp post here, and I'm gonna go person here. Can I do that? Sure. Okay.
That's not the scale.
Whatever. It's
Oh,
not
it's not
terribly.
Without the lamp post.
I don't know. Okay, whatever. Assume the scenario can be modeled with right triangles. At what rate is the length of the person's shadow changing when the person is 16 feet from the lamppost? Okay. First of all, 7 feet and 20 feet, my right triangle is not going to be using those dimensions or those lengths. Right? 7 feet and 20 feet, which means my triangle is how much?
13.
13, right? 20 feet is from here to here, and 5 feet is from here to here. or 7 feet is from here to here. So 13 is this length right here. Will that 13 stay 13, no matter what,
Yes.
as I'm walking? Yes, so this stays. Oop, this 13 stays. I'm gonna put a square around him. He stays. So we don't have to call him A. We can go ahead and plug in 13. All right. At a rate of 5 feet per second. So they're walking this way at a rate of 5 feet per second. Okay, what is this gonna involve, by the way? A squared, B squared, C squared, because are we talking about angles here or not? I think we're just talking about the sides, so A squared, B squared, C squared. Got it. A squared, B squared, C squared. Which side do you want to be side A?
Yeah.
What, this one?
Would you say that's
A?
nasty?
B, and C? Okay, so then what is 5?
5 is the
DRD.
A, B, T.
5 is gonna be, what? What did you say?
D, A, B, T.
dAdt. Okay, dAdt is the rate at which we're walking, right? dAdt is 5. Okay, B is 13. In my equation, okay, real quick. A, happy birthday!
Happy birthday.
Birthday.
A, can we leave him as A, or do we have to, can we plug a number in for A?
Leave him as A.
Because he's gonna change, right? B, can we make him 13, or we have to leave it as B?
13.
We can make him 13 because the 13 is not going to change, right? So in the formula, I can plug him in. C, will C change?
Yeah.
Yes, so I have to leave him a C. Okay, got it. So that's my equation. Things that I know that B is 13. I know that dAdt is 5. Assume the scenario can be modeled with right triangles. At what rate is the length of the person's shadow changing when the person is 16 feet from the lamppost? Confusion. What are we talking about?
Is that DCDT?
I don't understand how we find the shadow.
At what rate
Is it just-
is the length of the person's shadow changing? Well, doesn't this determine the rate of the shadow? Because the angle of the light. So they're asking for dCdt. They just asked for it in a really weird way. Because this angle or this whatever, the rate at that changing is going to change the same as the rate of the shadow changing. Okay, so we're trying to find dCdt. When the person is 16 feet from the lamppost, what does that mean? A equals 16. Just A equals 16. Okay. All right. We've got all of our things. We need to find the derivative.
13 squared.
Yeah? Okay. A squared plus 13 squared equals C squared. All right, derivative of A squared. 2A dAdt. Equals 13 squared. Oh, no, equals plus. Derivative of 13 squared.
No.
0. Equals derivative of C squared. 2C dCdt. Okay, we're trying to find dCdt. All right. 2 and A is 16 and dAdt is 5. Plus 0, I'm going to leave that off. Equals 2. We don't know what C is. We know what B is. We didn't even use B. Why did they give us B if we don't even use B?
Because we have to use define C.
We have to use it to find C.
Duh.
If A is
Part is obvious.
A is 16 and B is 13, and I can find C at that exact moment. So 13 squared plus 16 squared equals C squared. 169 plus 256 equals C squared. That is what? 20.6 is C squared? Okay, there we go, 20.6.
Scarf.
You gotta choke.
And then times dCdt. Okay. 2 times 20.6 is 41.2. And if I divide by 41.2. I don't know. This is
Okay.
no. 16 times 5 is 80. So this is 160 divided by 41.2 is dCdt.
3.88.
3.88. What per what?
Feet per second.
Feet per second. Yeah, it's changing at a rate of 3.8 feet per second. Yeah. That's maybe sounds right. Yeah. Not too bad. Do you need me?
Yeah, I wanted to see what I did wrong on 3-3 worksheet, cause I got not very good on it.
I don't know. I'll dig it out here in a second. Last one. An observer stands 700 feet away from a launch pad as the rocket is being launched. I'm going to do the same thing as same picture as what we had yesterday. Don't judge my rocket. I don't know what's going on here.
What is that?
It's a rocket.
Not very aerodynamic.
What do I do then?
You look like a tall house.
Yeah,
Like that?
yeah. Put little wings on it.
Little wings.
yeah.
Okay, now we're in
Add
business.
some windows maybe.
No.
Just like one.
No.
They don't put windows on a rocket because they'll
Just like
explode.
one. No, I want to see.
You're
what
a
the-
silly goon. Okay, so the base of my rocket is here, and whatever. I should make it go like this. Zoop, so the rocket's in the air, right?
Right.
And he's doing something like this. Okay, there we go. So we got a right triangle again, right?
Okay, Sammy has a
And my person is 700 feet away from the launch pad. Okay, all right, where's the 700 go? Shh. 700, bottom.
You want that one?
Will that stay 700? Yes, so I'm going to put a little box around him. He stays. The rocket blasts off and maintains a velocity of 900 feet per second. So 900 feet per second. So are we doing, assume the scenario can be modeled as a right triangle. How fast is the observer's rocket distance changing? All right, this is Pythagorean theorem again. Okay, let's give some names. What's A?
700.
Sure. B is the side. C is this guy. Okay, so let's talk about some things. The equation is A squared plus B squared equals C squared. All right, A. Can I plug 700 in, or do I need to leave it as 700? Or leave it as A? Plug it in. 700 will stay 700 no matter when that rocket goes, right? So this can change to 700. All right, B, will B change? Yes, will C change? So they have to stay as B and C. Do we know how that works, right? Okay, things that we know. We know that A is 700, which we've already plugged in, okay? We know that, what's 900?
But DB.
dBdt, if that's what we've named him. He is 900. Okay. Assume the scenario can be modeled as a right triangle. How fast is the observer to the rocket distance changing
At 2,400 feet.
at 2,400 feet from the ground? So what are we trying to find? How fast is the distance changing between?
dB dt.
We're trying to
We're
change.
looking for a C.
We're trying to find dCdt, right? How fast is this distance changing? dCdt. So find dCdt when the rocket is 24 feet from the ground. What's that mean?
That's what we plug in for B.
That's what we plug in for B. B equals 2,400. Okay. What would you like to do now?
C is 25.
Okay, so I heard Tate just say what? C is how much?
2,500.
Exactly. Yeah, 724.25. Yep. So he plugged A, B, and C in, or A and B into the Pythagorean theorem, found that C at that instant is 2,500, which we didn't already know, but he just figured it out for us. All right, now let's find the what? Derivative?
Yeah.
Derivative of 700 squared.
No.
0. You don't have to put 0, but I'm going to. Derivative of B squared.
2b.
2
dt.
B dB dt equals C squared,
2C.
2C,
CBD. ICD.
dC dt. Okay? All right, 0 I'm not going to worry about. 2 times B is 2,400. dB dt is 900. We got some big numbers going on here. Equals 2 times C is 2,500. And we're trying to find dC dt. Okay. Oh, I don't know what that number is. I know that this is 5,000. So I'm dividing by 5,000.
864.
864 is final answer?
Let's
864 is DCDT. What per what?
What is it?
Feet per second.
Feet per second. So this rate is expanding at that many feet per second. All right, now, if this is going 864 feet per second, is that number going to increase or decrease as the rocket gets higher in the air?
Decrease.
Assuming the rocket is not speeding up and they're going a constant,
Oh.
right?
Mm-hmm.
You think it's going to increase or decrease?
Decrease, definitely decrease.
I'm thinking decrease. Because it's gonna be like above you. Oh no, we're not talking about the angle though.
No, is it stay the same?
So it's moving from like here to here to here to here
So is
to
I
here.
think it slows down because it'll be right above you.
But it's still going up at 900 feet per second.
Yeah. But it'll be going like, yeah, I'm thinking it's going above you.
But it's actually not. It's still 700 feet that way.
Perhaps.
Like it doesn't veer over on top of you.
Right. But at a certain point, you're gonna be looking up.
It's about the distance,
Pretty-
not the angle.
I know. Why is this racking my brain so much?
I don't know either, actually. So I'm just making stuff up.
The distance, not the answer.
I wonder if it's speeding up. Because the length of this in comparison to this is not a whole lot, right?
Hey.
But the length of this in comparison to this is.
They're a brand. They're a band.
Exactly.
I think it's speeding up that distance. The rate of change of the distance.
Well, can't we solve for it? Use one of those fancy.
Well, just
derivatives?
plug in another number, right?
Yeah, plug in 6,000.
So it's gonna stay 9,000 no matter what, like this
Where's your
DPDT.
equation?
So let's do a smaller number. Let's do, hold on.
One.
Do this. Just do 7, 24, 25 for A, B, and C instead of 700, 400, 500.
Okay, you just confused me. I'm gonna do something else.
Oh, but we can't do that.
Don't touch that. Don't touch the merchandise.
Yeah, we can do that. We can do that.
It's speeding up.
It's speeding up. See, that's what I thought. The angle is slowing down, but the distance is speeding up.
No one believes tape.
The distance is
All
speeding
of
up.
a sudden-
Okay, whatever. 864. There you go. Beautiful. Okay, sorry for our banter, Daniel. We're done for the day.